Welcome back to Dave Does Math from Home. This is part 2 of our videos on section 6.4, volumes of rotation using the pipe method. I'm going to go directly into that example I promised in section 6.3. We're going to start right with that. The example was y equals 1 over x on the interval from 1 to 5. Which looks like this, from x equals 1 to x equals 5. This is the area that we were spinning around. And when we spun this around the y-axis, when we used the disk method, we had to use donuts because the region was separate from the axis itself, and that was kind of a pain because disks are always easier than donuts. And we had to split it in half. We had this sort of like break here because these slices went from x equals 1 to the edge of the function, and these slices just were a solid disk from 1 to 5. And it was really kind of exhausting. So we're going to do it again using the nice technique. This time we're going to slice this thing horizontally or vertically. Let me do a better vertical slice here. Okay, we are slicing this thing vertically, and we're going to spin this vertical slice around the y-axis, and we're going to see what happens. Again, the vertical slice around the vertical axis is going to give us a pipe shape, just like a rolled up piece of paper or a soup can, a hollow soup can without a top or a bottom. And the volume of such a thing can be thought of as a rectangle. If you were to cut it up one side and sort of unroll it so it laid flat, you could pretend it's a rectangle. The volume of a rectangle is length times width times height. I keep on saying volume of a rectangle. The official word is rectangular prism. Rectangles are two-dimensional. They don't have volume. They just have length and width. Rectangular prisms is what happens when you get like a 3D rectangle that has length and width and height. So we have a length and a width and a height. And we need to figure out what all these numbers are. The height I will start with as this dimension here. This is the height. It is a y value, and it is defined as 1 over x. So that's pretty straightforward. So we have h equals 1 over x. The length. This is the dimension that, if we're thinking about a rectangle, the length is going to go from here to here. But if we're thinking about this as a pipe, it's the circumference. I gotta get that in frame. It's the circumference. So the length is always going to be 2 pi r, because that's the circumference of this thing. And this is the radius from here to here, and that's just an x value. So this is 2 pi x. And the width is this little dimension up here. That's the thickness of our piece of paper. That's the dimension that we are shrinking down to absolutely nothing. And in the meantime, we're calling it dx. So the volume of my pipe should be 2 pi x times 1 over x times dx, which is 2 pi dx. X and 1 over x cancel. So the volume of my shape should be 2 pi times the integral from, we're going from x equals 1 to 5, from 1 to 5 of dx. the integral of dx is x from 1 to 5. Or you could, if you want to think about there being a 1 in here, you can. The antiderivative of 1 is x. However you want to think about it. You get an x here. So this is 2 pi times 5 minus 1, which is 8 pi. And we're at 5 minutes and 30 seconds. I feel like the last time I did this problem with the horizontal slices, it took me like 15 minutes. It was one entire video all by itself. It was just one giant, ugly, hideous mess. So here we are, doing the same problem in a much, much, much easier way in 5 minutes, while also talking for a while about how messy the other one was. I will let this serve as the illustration for why having two different techniques for volumes of rotation is a good thing. If we only ever had the disk method, then this would just get exhausting constantly. So, I want to do another example. Let's do y equals the square root of x. That's that. I want to rotate this around the x-axis this time. No, I think we already did this. The square root of x rotated around the x-axis is just bullet bill. We've done that one before. Let's do, oh, here's a good one. Let's do e to the x squared. E to the x squared looks like this. I want to rotate this around the y-axis. Between 0 and 1. So the shape we're going to get is probably going to look a lot like the one we started with in the first video. Kind of a shot glass looking shape. But the mathematics of getting there are going to be a lot more interesting. As usual, I'm going to take slices that are perpendicular, or in this case parallel to the axis of rotation, which will give me pipes. And the volume of those pipes is going to be length times width times height, because you can unravel the pipe into a rectangle shape. And the height is this, which is a y value, which is e to the x squared. And the length is, if you unroll this thing, the length will be the circumference, which is 2 pi r, and r is a x value. So this is 2 pi x. And the width is the thickness of the paper, that tiny little thing that we're shrinking to almost nothing. That's going to be dx. So, the volume of my shape, the volume of the pipe, when you put all this together, should be 2 pi x times e to the x squared times dx. And so the volume of my shape is 2 pi times the integral from 0 to 1 x e to the x squared dx. So, one of the really nice things about this technique is that under normal circumstances, e to the x squared is not something that we could integrate. If you were trying to do an e to the x squared thing by itself, that's not integrable because it's a compound function and compound functions aren't safe. The only way we can integrate this compound function is by looking at the inside, the outside, and the other. The inside is x squared, the outside is e to the blob, and the other should be x dx. So we can set w equal to x squared, and then dw will be 2x dx. So if I need to put a 2 in here, I can pretty much just borrow this one from right here. I don't have to put the 2 inside and the 1/2 outside. I can just move this 2 in here. So now the other is 2x dx. That's been taken care of. I already had that 2 sitting around, which was nice. And I can rewrite this integral. Pi stays out front. This is the integral from x equals 1 to x equals 0 to x equals 1 of e to the w dw. And the integral there should be pi times e to the w from x equals 0 to x equals 1. I've run out of room officially now. I guess it's time to erase this stuff. I'll try to snake across the middle here. So, first I need to unsubstitute for w. This will be pi times e to the x squared from 0 to 1, which is pi times e to the 1 squared minus e to the 0 squared, which is pi times e minus 1. I have no idea what this is, but it's the volume of this shape. It's probably going to be 1.7 times 3.14, so it's probably going to be like 5.5-ish, something like that, maybe close to 6. I don't care what the actual number is. I just like that I can express it without using variables or integrals, which I think is very nice. So this is one of the advantages that the pipes technique has. We saw sort of the first advantage in the first example we did, where we did a problem very easily that using the other technique took us 15 minutes or whatever. And here we have a problem that because of this e to the x squared business, because of the compound function here, this is something that we would not be able to integrate unless we introduce an x piece from somewhere else. So that's a neat trick, I think. I'm going to see if I can squeeze in one more example, because I want you to see what it looks like when we rotate around the x-axis using this technique. We haven't done one of those yet, so let's see if I can do that fast. We're at 14 minutes. Tick tock. So let's say y equals x squared. That would be this guy on 0 to 2. But I want to rotate around the x-axis. So I'm taking this area, spinning it this way. This is a problem that I think we did earlier with disks. This problem is very easy with disks. You could cut this thing vertically to make nice disks. You would go on x from 0 to 2. I want to do this one with pipes so that we can see what that looks like. If we're doing this problem with pipes, we want to slice it horizontally. The volume of the pipe is still going to be length times width times height. Following the tradition of several other examples we have done, I'm going to say height is this dimension, which is not exactly an x value. It's an x distance, but the x value here is like this, and that's not what I want. I don't want this x value. I want 2 minus this x value. Because that'll be what's left over there. And I need a length. The length will be the circumference, 2 pi r. R is going to be this distance, which is a y value. So this will be 2 pi y. And I need a width. The width is going to be this tiny little sliver. And since that's a tiny little vertical sliver, we're going to call that dy. So, if we're integrating this with respect to y, we need to switch this into something to do with y's along this curve. So if we solve this, we'll have x equals the square root of y. So that's how we're going to do the h. 2 minus the square root of y. So the volume of my pipe is 2 pi y times 2 minus root y times dy. And the volume of the shape I get from that should be 2 pi times the integral of, I'm going to distribute this, 2y